In this lecture, we'll continue to talk about the big topic, which is fast Fourier transform, and in particular, we will talk about the theoretical development of the fast Fourier transform, FFT, for the case where capital N, which is the number of sample data point, capital N, can be expressed as the product of the two integer R1 times R2, where R1 times R2, each of the R1 or R2 could be any integer number. So in particularly, for this specific case, we want to see what happens when R1, let's say, equal to 4 and R2 is equal to 4. Now, the motivation behind this chapter is because up to now, we always restricted that the number of sample data point, capital N, has to be expressed in terms of 2 raised to the power r, where r is any integer number. But here we begin to remove that restriction. What? Cell phone? I already turned it off. So should start again. Okay, like I told you before, in this particular chapter, we would like to consider the situation where the number of data point, capital N, can be expressed as the product of the two integer R1 times R2. Now, if you remember, as up to now, we always consider the case where capital N be expressed in the form of 2 raised to the power r, where r is equal to an integer power. Now, if that is a formula, then the value of the capital N will be restricted to be equal to either 2 or 4 or 8 or 16 and 32 and so on. But that depending on the value of r equal to 1, then capital N is equal to 2. If r equal to 2, then capital N equal to 4. If r equal to 3, capital N equal to 8. And if r equal to 4, then capital N is equal to 16. However, as you can see, what happens if we have a data point where capital N is equal to some other number, let's say equal to 12 or 15. In that case, then we will not be able to express in the form of 2 to the power r. So for that reason, in this case, we want to consider the situation where the number of sample data point, capital N, can be expressed as the product of any two integer number. Now, the index N can be given according to equation 38. Actually, this equation is based on the assumption that the number of sample data point can be expressed in terms of a product of the two integer R1 and R2. As you can see, in that situation, then the value for the index N will be given by equation 38, and the value for the index K will be given according to equation 39. Now, later on, you will see that we can generalize this idea to a more general situation. For example, we say, what happens if we have the number of sample data point N can be expressed as the product of the 3 integer R1 times R2 times R3. You see? And this concept can be generalized to up to even M product, R1, R2, R3 up to Rm, as you will see later on. So for the case of capital N equal to R1 times R2, the value for the index n and k are given by equation 38 and 39. If, on the other hand, the capital N is given by three product R1 times R2 times R3, in that case you will see this formula can be generalized to N equal to 1 times N0 plus R1 times N1, and then plus R1 times R2 times N2. Similarly, for the situation where capital N is equal to the three product R1, R2, R3, the equation 39 for the index k can be generalized to k is equal to 1 times k0, 1 times k0 plus R3 times k1 plus R2 times R3 times k2. And I hope you begin to see the pattern, because for, let's say, the product, the capital N is equal to the product of R1 times R2 times R3, you can see the first term here have the coefficient equal to 1 for N, and then the second term have a coefficient R1, and the next term have a coefficient R1 times R2, and you can see the pattern. Whereas for the index k, the pattern is similarly, the first term has a coefficient equal to 1, the second one have a coefficient equal to R3, not R1, and then the last term will have the coefficient of R2 times R3 instead of R1 times R2. But the pattern you can see from n equal to the product of two integer to three integer can be very clear. Also, according to equation 38 and 39, for the situation where capital N equal to R1 times R2, the value of N1 and N0 are given by equation 40 and 41. Actually, and also the value for the index K1 and K0 is given by equation 42 and 43. Now, if you generalize to the situation where capital N equal to three product R1 times R2 times R3, then these two formula for N1 and N0 can be generalized to the formulas look something like this: small n of I minus 1 equal to 0, 1, 2, blah 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 blah, up to R sub I, and then minus 1. And that formula will be valid for the subscript I between 1 and M. Okay? So for a more general situation, equation 40 and 41 can be generalized like that. And then similarly, for the more general situation, the formula for the index K1 and K0 can also be generalized to something like Ki equal to, can be 0 or 1 or 2 all the way up to R of M minus I, and then the whole thing minus 1, where in this formula the index I is between 0 to M minus 1. So equation 42 and equation 43, which is applicable for the situation where capital N is equal to the product of two integer number, can be generalized to the situation where the capital N is equal to the three product integer R1, R2, R3, or even up to Rm, is the way I just describing here. But for this chapter, let us try to focus only for the situation where capital N is equal to the product of R1 times R2, and let's see what happened. Okay, now in this situation, let us consider, remember we have a term called W raised to the power N times K. So this small index N can be expressed in the first parenthesis, as I show you there, which is N is equal to N1 R1 plus N0. And the reason is because based on the previous definition, see, if you remember the definition of N is equal to N1 R1 plus N0, and then K equal to K1 R2 plus K0. So based on the definition given in equation 38 and equation 39, we make some conclusion. Like for example, if you give the smallest value for N, the smallest value for N could be 0. Okay, and that value of N equal to 0 will corresponding to N0 equal to 0 and N1 is equal to 0. Because if you substitute N0 equal to 0 and N1 equal to 0 back into the previous formula for N, you can see very clearly equation 38 will give N equal to 0 when N0 equal to 0 and N1 equal to 0. So that is the smallest value N can have. On the other hand, the biggest value that N can have will be occur when N0 is equal to R1 minus 1 and N1 equal to R2 minus 1. Because based on N0 equal to R1 minus 1 and N1 equal to R2 minus 1, we can go back to plug into the formula for N, and we will see after you expand this formula, this will become R1 times R2 minus 1. So, which is obviously true because in this particular chapter, if you remember, we consider R1 is equal to 4 and R2 is also equal to 4. So that basically means the value of capital N is equal to R1 times R2 is equal to 16. 4 times 4 is 16. And because the capital N is equal to 16 data point, therefore the smallest value of the index N you can have will be 0. That corresponding to N0 equal to 0 and N1 is equal to 0. And also because capital N is equal to 16, and therefore the largest value that you can have for N will be equal to R1 R2 minus 1, which is very obvious because R1 times R2 is 16 minus 1, which is equal to 15. So let's take a look and see about the formula that we have developed earlier in the informal development for the fast Fourier transform. At that time we say